Thank you, Liska. I'd like to start by very quickly introducing myself. My name is Frans van Buul. I work at AxonIQ. At AxonIQ, we all have mugs, and my mug says I'm not the sales guy. It tells a little bit about my role. My role is to tell the world about all our products, but I'm also a developer myself, so not a typical sales guy at all. You see my contact details on this slide as well. Please do feel free to use them and reach out if you have any questions related to this presentation or anything else. Since AxonIQ is such a new company, I'd like to introduce ourselves as a company as well. We were founded in July this year, so just a few months ago. We had our official launch event last month. Currently, we're about 11 people based in Amsterdam. And as you probably know, we fully focus on the open source Axon framework. And actually, one of our founders, Allard Buijsen, was the initiator and main author of the framework. At AxonIQ, we have two main lines of business. One line of business is to provide all kinds of services around Axon framework, like support, training, consultancy engagements. And the other line of business, where the EventStore falls into, are our commercial software products that can be used in addition to the open source Axon framework. The roadmap for these products looks like this. So we're currently talking about the EventStore. That's the first of our products. Following the EventStore, we will be working on a messaging platform and on a management monitoring and analytics offering. Those will be released in 2018. And in parallel, we're working on a separate GDPR module. We'll be running a separate webinar on that module in a couple of weeks if you are interested in learning more about that. But for now, we'll focus on the EventStore only. The agenda for today. I'll start with a quick intro about event sourcing. I'll keep that quite short because I think most of you are fully aware of what it is and why you would want to do that. But I wanted to revisit it very quickly anyway so everybody can follow the rest of the story. And then I want to systematically look at the kind of requirements that you would pose on any form of event storage. Once we have those requirements in place, I'm going to evaluate those against some well-known options for event storage, like Relational Databases or Kafka. We'll see that most of these existing solutions fail at some of these requirements, and that was the driver for us to create our own event store. So next we'll look at the architecture of the AxonIQ EventStore, and then we'll end with a couple of slides on how you could get started with this product yourself if you're interested in it. Starting with event sourcing. Event sourcing essentially is a specific kind of event-driven architecture. And event-driven architecture in general simply means an architecture that focuses on events. That's really hot these days. For instance, we see a Gartner report here about strategic technology trends for 2018, where they mention event-driven as one of the key trends. And the background for that is really clear. Event-driven architecture is popular because it works really well with distributed, diverse, potentially unreliable systems, integrating across organizations, and it allows for great flexibility. If your requirements change or you want to integrate new systems later on, event-driven architectures make that as easy as it can be. Event sourcing is essentially an event-driven way of dealing with persistence. So it's about how to store your objects in a database. The traditional way of persistence would always be to just store the current state into a database. In Java, using JPA would be a very popular option to do that. And then you start doing create, reads, updates, and deletes on your objects as changes occur. Event sourcing is a totally different approach to persistence. Instead of storing the current state, the thing that you're storing is all events that have led to some state change, which also means that there cannot be any state change except through events. These events themselves are being distributed to other nodes as well as being persisted to the event store. And this also means that accessing the current state becomes a little bit more complex, because in order to access the current state, you cannot read it directly. Instead, you need to read all those relevant events and then replay them to get access to your object again. So that's quite a lot of complexity. And as always, if you introduce that kind of complexity in your system, that needs to have some kind of justification. And there is. So some key benefits of event sourcing are, first of all, that if you use event sourcing, you can be absolutely 100% certain that your events fully cover all changes, which is not the case if you use event logging as a thing secondary to your primary persistent mechanism. As a result, that gives you a perfect audit trail. You can revisit exactly what has happened to your business objects. This historical data is great input for analytics and machine learning and all these other hip new things. It's also great input for debugging because you can know exactly what happened in your system at any point in time and recreate that situation. If you have separate read models, like in a CQRS-based architecture, having event sourcing, make sure that you can always replay your old events and recreate new models. And finally, a great thing about event sourcing is that it captures the intent of change rather than just the change itself. For instance, suppose that you have a customer database and you're going to update an address record. In a traditional CRUD-based system, it would just be a change. But in an event sourcing system, you could start capturing the difference between correcting an address that was simply wrongly registered versus registering that a customer has actually changed address, that they have moved, which are from a business point of view very different things and may lead to different actions later on. So there is great value in event sourcing of capturing those differences in intent. So that's very shortly about event sourcing. So if you use event sourcing, then by definition, you need to store your events in some place. We call that, generically speaking, an event store with lowercase letters. So let's have a look at the requirements you would pose on that. On a very high level, it's just two things. It's reading events and writing events. Now, if you would zoom into that reading first, there are actually two kinds of reads. So there is the case where you need to read all events belonging to a single aggregate or single object. That's the thing that you would be doing in an event source repository prior to making some other modification on that object. And the second case is that you would want to read all events either since the absolute beginning of EventStore or since some point in time, but disregarding the particular aggregate that they belong to. So this is the kind of thing that you would need for replaying read models or other types of event handlers. Now, a shared requirement on both types of reads is that you want to read the events back in right order. Otherwise, the replaying thing will not work successfully. So there are a couple of read requirements. On the right side, the key thing that you need to do is append events. So you need to append them to the end of your current set of events. Which also means that there are a couple of requirements which are not requirements. So we strike them through here. You don't need to insert events at a random point in time. You don't need to be able to update events. Events are absolutely immutable. And there's no reason why you would delete events. You would keep all events. Which means that this write event requirements is actually not really right. It's more append events. That's the key requirement. Now, to get some more requirements, let's zoom into a specific case. Here's a very small sample case where we are creating a bank account. Bank account starts with a zero balance and there is no credit limit, so you cannot withdraw more than is ever deposited on the account. A second event related to that same bank account could be the deposition of thousands of dollars or euros of money on that account. So after that, we could again withdraw money from that account. So in this case, 600 as an example. And what would happen at that point in time where the withdrawal takes place is that the application logic would reconstitute the bank account aggregate by replaying the first two events. Then it would conclude that there is the current balance is 1,000 because we started with 0 and just deposited 1,000. It will then evaluate whether 600 can be withdrawn, and it would say yes to that because 1,000 minus 600 is more than the limit of 0. So we're fine. So this all goes well. Now let's have a look at this case. Suppose that you have a distributed system of multiple nodes, and a command to withdraw money is done in parallel on two nodes. And on one node, we're trying to withdraw 600, and on the other node, we're trying to withdraw 700. Now, if these actions take place in parallel and are approved in parallel, what would happen is that 1,300 will be withdrawn from the account, which is a violation of the business rules on that account. Now, the way you would deal with this in an event sourced system is that the sequence numbers belonging to events in the event store for a particular aggregate would always increase by 1. So we have had sequence number 0 and 1 when creating and depositing money. The next sequence number will be 2. And if 2 nodes both try to insert a new event with the same new sequence number 2, the event store can and should detect that there is some kind of violation there, and it should not approve both inserts. It should just be 1. So appending events actually has one specific requirement there. We need to be able to validate aggregate sequence numbers. And in a sense, this is a consistency requirement. I've highlighted the C of consistency because this is one of the 4 asset properties of databases. And we're going to see some of the other ones as well later on. Another more subtle requirement on this is again starts with the same example. We created a bank account and deposited some money on this. A specific thing about this bank account is that it's not just a money account, it's an investment account, so I can use the balance on that account to buy some shares. So for instance, I could buy 5 shares of XYZ Corp at 100, which means that 2 events would be processed on this aggregate. So it would effectively be a withdrawal of 500, but then I would also be adding 5 of those XYZ shares to my account, so 2 events. Now what's very important is that these events either succeed together or fail together. But if you have just one of those 2 things being committed to the database, bad things happen. So if we go back to the requirements, we already had to validate aggregate sequence numbers requirement, but we also have a requirement that we need to be able to append multiple events at once. In asset terms, that's an atomicity requirement. That's for the write side. What this means on the read side is that we need to have a corresponding property of just reading the committed events. That's in asset terms called isolation. And since we're doing the asset thing now anyway, let's complete it with the last one, the D. Whenever an event has been committed to the database, we need to make sure that it's actually protected against loss in a reasonable manner. That's called the durability, the D. So these are also requirements on an event store. Now, revisiting the bank account example again, bank accounts tend to exist for quite a long time. I've had mine personally for about 25 years. Now imagine what happens with your events in that time. Many events will be stored for that same aggregate, which means that reading your aggregates by physically replaying all those events whenever you need to do something becomes very performance intensive. So in these particular cases, you don't want to use just events. There also has to be the notion of snapshotting. So at regular intervals, you would not just store an event, but would store a representation of the current state of the aggregate. And then you can make reads much more efficient later on because you can start reading at a particular point in time where you created a snapshot and then only applying those events that occurred after the snapshot was created. Taking this back into our requirements means that this is actually not just about events. We need to be able to deal with both events and snapshots. And this changes our read requirements, in fact, because the requirement of reading everything for an aggregate becomes a requirement in 2 different flavors. So one is that we read the latest snapshot and then all events coming after that snapshot, and that's the operation that would normally be used by an event source repository. But still, we would also want to be able to read all the events for auditing purposes and get all the value that we want to have from event sourcing. Now, we just looked at a number of events in the context of a single aggregate. There's of course also a scalability concern in terms of the total number of events over all aggregates. If we assume that there are thousands of events per bank account and we have 1 million of bank accounts in our system, which is not unreasonable, then you would literally be talking about billions of events. Now, in general, database systems and all kinds of collection operations are dependent on collection size. Table scans are linear in n, and tree lookups are dependent on the logarithm of n, but there's always some kind of dependency. And for event sourcing, that's not what you want. For event sourcing, given the fact that these events are never deleted and they just grow, what you need is that performance is a constant function of the number of events already stored. So let's add those things to a requirements list. We want to have a constant performance in terms of writing as a function of storage size, and at the read side, you always want a constant performance. But especially, it's also important that you optimize for recent events. With event sourcing, it's far more likely that recent events are being accessed again than very old events. So the database, the event store should know about that and take that into account. Now let's have a look at one final requirement before we start evaluating some systems against these requirements. The final requirement has to do with a multi-node setup. So here we have two nodes, node 1 and node 2, that are communicating with one another in terms of events. And then we have this event store that's shared between them. Now, whenever node 1 generates some events, they have to be stored in the event store, but somehow they also need to get to node 2. Node 2 may, for instance, be a read model in CQRS terms that's going to update some of its own data models according to these events. So how do these events end up in node 2? Well, one approach is to do polling. So node 2 would do poll to the event store every second or every 5 seconds or however you configure that, and then the new events would be sent back to node 2. This is a workable model. It's actually how Axon Framework currently implements it. It's also quite ugly. There is no real-time push, so you introduce some delay. There are some unnecessary CPU cycles being spent on that polling. So it's workable, but it's definitely not ideal. Another model would be to have a message bus in between node 1 and node 2. For instance, a RabbitMQ or something. And node 1 would then publish its events in two places. So it would store them in the event store and also publish them on the message bus. So node 2 can communicate, can find them. Again, that's workable, but there's also a big risk. What you want to have for consistency purposes is that the exact same events are being stored in the event store and published on the message bus. But there's no real way that you can guarantee that. It could be that node 1 stores its events successfully on the event store and then tries to publish them on the message bus, and something fails, or the other way around. So it's workable but not ideal. What you would like to see ideally is that the event store itself can push those events. So whenever events have been committed to the event store and the event store has acknowledged them, it would also publish those events to any reader that's attached. And then you would get the events in real time. You don't need additional runtime component like a message bus. It's just a very simple and efficient setup. Conceptually, this is in fact implemented in Axon 3 because the event store interface there is a subclass of the event bus. But technically, it's very hard to implement with the relational database. So that's why we do the polling instead. But in an ideal world, this is what you would do. So that adds one more requirement to our events list. It actually has to do with our ability to read all events since a particular point in time. We need to be able to read all events since a point in time and then continue to read and have new events pushed on that channel as they occur. So now we have this nice list of boxes to tick on various technologies. We have looked at 4 different event store options. We've looked at relational databases of any vendor and MongoDB. Those are the ones that are currently being supported by the open source Axon framework and the ones that are being used by most of our customers. And we've looked at 2 potential alternatives. Kafka is being mentioned a lot as a way to store events permanently. Cassandra is mentioned sometimes. And the reason we've looked at them is that we really didn't want to create an event store. For us, the messaging platform was the more interesting thing to start working on. But we cannot create that reliably if we don't have a reliable, scalable place to store events. So we need an event store first. So we've looked at a few of these options, and then after that decided to build an event store for ourselves for reasons we're about to see. Looking at databases first, relational databases. The big pros of this technology are, of course, that it's very well established. We know some institutions say thou shalt store all the software or the data on Oracle and nothing else. And they have great support for transactionality, which helps us to do the sequence number validation and storing multiple events at once. So there's a lot going for relational databases, and this is actually what most of our Axon framework users are currently having in production. The big issue with relational databases is scalability. They work fine if the storage size, the currently stored events, is relatively small. But as that grows, you will see that throughput in terms of writes and read efficiency will go down dramatically. And there are a couple of reasons for that. First of all, databases tend to be fast if they can be kept in memory. And as the data size grows, an ever smaller percentages of the database will reside in the buffers. There's no real way to optimize for accessing recent events in a relational database. The general assumption is that every record in a table is equally likely to be accessed for read. And of course, it maintains an index on all these events, which is required to be able to find the events belonging to a certain aggregate. But maintaining that index on all these events becomes ever more expensive as the number of events grows. So the absolute numbers on this chart are not that interesting. We've actually suppressed them on the vertical dimension because you can, of course, change the dimensions of this graph by adding more memory or adding bigger, faster disks. But what you cannot really change in a relational database is the shape of this graph. By its very nature, performance will go down if the number of events grows, which is definitely a problem if you're doing event sourcing in high performance environments. So big cons of a relational database, first of all, the scalability problems. There are actually some more. The idea of pushing events is hard to do in relational databases. There are some very vendor-specific options working with triggers and built-in queues. There's no generic clean way of doing that. So there are a couple of boxes on our requirements list that are definitely problematic for relational databases. Looking at the second candidate, Mongo, great, well known for its horizontal scalability through sharding. Also attractive potentially because it could do analysis on events rather than storing events as a blob. You could actually do some querying. And now MongoDB is document oriented. So the big question that you get is, how do events map to documents? And the naive answer to that question would be to say, well, an event is a document. It's one-on-one. Now, once you start having multiple events, you would get multiple documents. And you get into trouble as soon as these events are becoming a transaction, like we saw in the investment banking example, where we need to store multiple events altogether or not at all. In Mongo, we're fully document oriented, and it has some transactional guarantees, but they only operate on the single document level. You cannot do things on multiple documents in MongoDB and still maintain transactionality. So that's a big problem. So if you care about that integrity check, you're kind of forced to do this. So instead of having a document per event, you're going to have a document per transaction. And that transaction document would actually contain multiple events, which is possible and actually implemented in Axon Framework 3, but it's also very ugly, and it also reduces your possibilities to efficiently query those events and actually use the fact that MongoDB could understand that structure. So the cons here, these document transactions. Another thing, the event push, just like with a relational database, we don't have that in Mongo. And there's also, it's a little bit more of a detail, but there is no way to create a global sequence number, which is problematic when reading back all events for replay purposes. So again, with Mongo, we have some very clear red marks why this is not meeting our EventStore requirements. Having a look at the first contender, Kafka. Pros, it's totally messaging focused, which is exactly what we need, and it's known to be extremely scalable. So two very good things, and I guess very understandable why people are looking at it. Suppose this is your set of events in Kafka, where the letters represent particular aggregates that these events belong to. One of the things that you need to be able to do is to pick out specific events for a single aggregate, in this case B. So how can we do that? Kafka doesn't have general indices that we can use to look up these events. So a very naive approach would be to simply scan all events and then filter them and then just return the ones that are related to B, which is possible, but of course it doesn't scale well. Its performance would be linear in the number of events already stored. So this is not going to work. Now, luckily, Kafka has this option called topics. So we could split our storage into various topics, create a topic per aggregate, and this would allow us to efficiently read the events belonging to a particular topic. Now, looking a little bit into how this works, a topic in Kafka is a logical unit. It spans multiple machines, and physically it's represented by partitions. So partitions are on a specific machine, and a topic could be live on one machine, have one partition, or be split over multiple partitions. These partitions themselves consist of one or more segments. This is crucial for the scalability of the number of events. Every partition physically has an associated directory on the file system, and these segments have two files, a log file and an index file. Key thing here is that this doesn't scale to millions of aggregates. You can clearly have thousands or 10,000s of files, but millions or tens of millions of aggregates represented by separate file structures doesn't work. It also means it's quite slow to create new partitions, because there's a lot more work being done than simply storing a new event. So if we look back at Kafka, it is extremely scalable, but we should nuance that a little bit. Kafka is extremely scalable in the total number of events, but it's not scalable in aggregates. This means that it's effectively not usable for event sourcing, except in those rare cases where you would have less than 10,000 aggregates or so in your entire system, but those are very exceptional cases. Last contender, Cassandra. Quite popular these days, known to be extremely scalable, works well globally, can have multiple global data centers. It has a peer-to-peer architecture, so you don't have this single master, that's a single point of failure. It has very tunable consistency, so maybe we could tune it to have the consistency needed to be an event store. So it has a lot going for it, just like Kafka actually. To see the problems with Cassandra, let's have a look again at this problem with two competing updates, where the event store should signal that there are two same sequence numbers and should deny the second transaction. In Cassandra, this problem is particularly difficult because we have this multi-master setup. So we could have two nodes that have both the same current state and that both get a new event with sequence number 2. And somehow, even though we have this setup, they should be able to detect the collision. So how can you do that? Well, Cassandra actually has an option to do that. It's called a lightweight transaction, LWT, and it's in the Cassandra language. It's being signaled by the if not exists clause. So here we see how this insert would happen, and then it would actually functionally do exactly what we expect. So this would work. There's just one drawback. Just quoting from the Cassandra manual itself. This is a very specific functionality. It requires 4 round trips between all replicas. So performance is affected, and it's actually something you should reserve for very particular situations. But in event sourcing, this isn't a particular or exotic situation. This is the core situation that you're having each and every time. So for that reason, in fact, Cassandra is just a mismatch with event sourcing. It can offer the required consistency, but at a very high price, and it's like a kind of exotic functionality within Cassandra that shouldn't be a primary thing to use. Interestingly, Netflix is using Cassandra for event sourcing. So if you're interested in hearing a different point of view and some of the problems that they have ran into, you might have a look at this presentation as well. It's really great. So since we evaluated all these contenders and saw some problems with them, we decided to build our own event store. So I want to continue by telling you a little bit about how that works. The key things to understand about EventStore: first of all, it's built in Java from scratch. The distribution is actually a jar file that you can run in any Java 8 or 9 environment. I'm proud to say that this product has zero flexibility, and that's a good thing. It's purpose-built for event sourcing. It's not a general purpose database. It manages files directly. There's no underlying database system or anything. It just writes to files. And it has very open interfaces where we support both HTTP with JSON as well as gRPC, which is Google protobuf on top of HTTP2, where we would also always recommend gRPC for high performance use cases. Some of the highlights: first of all, the event store is append only by design. So we don't have any deletes or updates or inserts. And that makes the event store simpler. It also means that we don't have the overhead of all kinds of locking mechanisms. We don't need to lock existing events, for instance, because they can never change. So that's one of the key things. The event stream, so the total set of events we store in our event store is split into segments. The segments can be of a configurable size. Do we expect them to be like 0.5 GB or something in that order of magnitude? Basically, this is the same notion that we also saw in Kafka, and it allows us to keep everything scalable and store arbitrarily large set of events. We have built-in support for snapshots. So snapshots are technically supported in a way very similar to events, but they have their own segments. And of course, on reading back, it has built-in functionality to find the latest snapshot and then read all events after that snapshot. For efficiency purposes, it's important for us that we can very quickly find events belonging to a certain aggregate ID, ordered by sequence number in any of those segments. And to make that work, the data structure for each segment actually consists of 3 files. So there is the data itself, then there is an index on that data, which is by itself rather standard, and then there's also a Bloom filter. Bloom filter is a specialized index, and what it does is that given an aggregate ID, it will either tell us that it's definitely not stored in that segment, or that it may or is likely to be stored in that segment. So the reading algorithm first checks the Bloom filter, which is very quick. And if it says no, then the reading algorithm can just go on. If it says yes, then it will check the index to see if it's actually there. And if so, on what position in the data file it can be found, and then it will read the actual data from the data file. So it's an extremely efficient way of finding the events belonging to a particular aggregate in the segment. Another particular thing about searching or reading algorithm is that we will always read backwards in time. So we will not start with the oldest event, but with the newest event and go back segment by segment. This optimizes for the fact that in event sourcing, it's more likely to read new events than old events. In that same spirit, we also support a notion of storage tiers. So recent blocks or recent segments are being cached in memory, so they can be accessed very rapidly, whereas the older ones are stored on disk. On future versions, we expect to support some more storage tiers. For instance, you could use more cheap network-based storage for very old stuff and store some more recent segments on the local disk and the very most recent ones in memory as well. So we can very much optimize for this use case. Now the event store, of course, operates in a cluster that's needed primarily for reliability purposes, so you don't get into trouble if one node goes down. So we support cluster setup. What we've chosen to do is use a floating single master model. So we don't have the peer-to-peer model that Cassandra implements, but at any point in time, one of the nodes is the master, and if that node goes down, the other nodes will start an election process and let one of the other ones become master. The client always needs to go to the master. If it doesn't go to the master initially, that node will refuse the request and tell the client where the master can be found. Benefit of this approach is that we don't have the problem that Cassandra has, where it's not really efficiently possible to validate sequence numbers upon appends. Writes are being acknowledged to the client when a write quorum has been reached. This is defined as the half plus one of the nodes. So in this case, with the 3-node setup, either node 1 or node 2 should confirm the write to node 3, and after that point, node 3 would, as a master, confirm the transaction to client. So that's how our clustering works. We've of course run some benchmarks on this, and the key thing is that our performance is stable as a function of the current storage size. The current chart goes to 100 million events. We've actually tested it with multiple billions of events. It's just not on the chart, but performance always remains stable. It's simply that case by design. Now, if you're interested in getting started with this yourself, first of all, of course, you need to obtain the software. The software is currently in beta stage. We are actively running a couple of proof of concepts with interested customers, but we would like to run more. So if you're interested in this, please contact me, and then we can have a discussion and see how we can start a proof of concept in your situation. The software itself is commercial closed source software, so you will get a jar from us, but the client itself is open source. You can find it on GitHub and also include it in your Maven projects. Currently, the client is focused on Axon 3 or not using Axon at all. There's no Axon 2 client yet. If you would have an Axon 2 requirement, please let me know and we'll find a way to solve that. And now, if you are, once you have the software and you actually want to start using it in your software, the way to do it would be to do this. On the line above, we see how you would normally configure a JPA event store, database-based event store in Axon 3. So you return an embedded event store. If you change that to the 8 lines of code below, that would actually activate the AxonIQ EventStore in your application, and you're done. So it's a really easy drop-in replacement with very low implementation costs. That's what I wanted to tell you about EventStore.